Morning, everybody. Welcome to our webinar on printing the impossible with composite technology. Before we start, I have a couple of housekeeping points. We've not got a scheduled fire alarm here, so if you hear any ringing noises, we will be running. Secondly, if you have any questions, please feel free to enter them in the Q&A box. You can find this on the right-hand side, and then we'll do our best to answer these at the end of the presentation. So please populate as we're talking through the content. So my name is Mark Dickin, and I'm the engineering manager for additive manufacturing at Ricoh UK Products. My colleague Enrico and I are going to talk to you about new opportunities for high-performance polymer-based composites. So before we take a deep dive into the subject matter that we're going to talk through today, I wanted to share a little bit of information about what we do at Ricoh UK Products, and I've got a quick video to show you. This is a little bit clunky, so please bear with me.
Ricoh UK Products Limited is where Ricoh brings together its customers and partners to optimize today's world of print and to influence the digital print applications and services of the future. With operations in both Telford and Stirling, Ricoh UK Products provides a world-class customer experience that demonstrates digital manufacturing and showcases the latest technologies that Ricoh has to offer. We regularly welcome new and existing customers and partners to our facility to share our knowledge and work together to drive innovation in the world of print. Over 35 years, we have established a strong manufacturing and innovation heritage. This has been driven by our commitment to sustainable development, engagement in continuous improvement, and lean manufacturing approaches. Today, both of our operations employ the very latest digital manufacturing applications as part of the fourth industrial revolution. To continue our digital transformation journey, our investment in production and process automation is laying the foundations to connect Ricoh across the end-to-end supply chain. Ricoh provides a range of digital services that can optimize business processes through data analytics. As an organization, our employees are at the heart of everything that we do. Our core values help us to co-create new, shared value with our customers and partners. Our Customer Experience Centre is the focal point for our co-creation and innovation activities, enabling us to engage with industry partners from around the globe on a peer-to-peer, expert-to-expert basis. As such, the Customer Experience Centre represents a unique, shared knowledge creation hub where we influence digital print applications and services of the future. Meet our experts and understand how we use the technology in-house to co-create with our customers and partners. Discover how we can see things differently for you, helping to streamline your business operations and create productivity. Let's work together to optimize the print of today and influence digital print applications and services of the future.
So hopefully you'll appreciate the scale and the diversity of our operations here at Ricoh in the UK. You'll see many applications where we've used 3D printing through the video in our marketplace factory. So moving on to our 3D printing business. Ricoh are extremely active and working on multiple initiatives in the 3D space. First off, we have our commercial entity, which is the print service. Our USPs here are mainly the Ricoh SLS polypropylene material and our composite part offering, which we're going to talk through today. We then have the latest new Ricoh hardware development, which is our metal binder jetting system focused around printing aluminium parts. This is in the R&D phase and due for commercialization in 2025. We're currently setting up a customer experience center as we speak, and we will be having an opening ceremony early 2023, which all people are invited to. We've also been developing our own resin-based printer for the dental industry, and also using a similar technology to metal binder jetting, but for ceramics. In the US, we have a Ricoh AM team with a focus on point of care services within hospitals, printing anatomical models from patient DICOM data. So it's really quite diverse. And then finally, we have a collaborative project working with Impossible Objects, utilising their composite printing technology, which is available through our print service. This will be the focus of today's presentation. So before we start getting into the technical detail, you might ask yourselves, why is Ricoh and Impossible Objects working together? There's a number of reasons. Ricoh are extremely interested in the Impossible Objects technology because it has a lot of synergies to the 2D printing process, which is part of the Ricoh's core business. We understand toners very well from this type of business, and these types of materials process very well on the Impossible Objects technology. We've also been extremely impressed with the quality and the strength of the components printed. For those of you who do not know Impossible Objects, they are based in the US and took the opportunity to work with us to obtain a presence in the European market, initially via our print service. We're also looking at another project where we're looking to integrate Ricoh technology, such as inkjet heads, into the next generation of machine. So moving into the detail now. Composite-based additive manufacturing, also known as CBAM for short, is a unique form of continuous fiber powder-based printing, which produces sheet fiber reinforced parts, both in carbon and glass fiber, fused together by thermoplastic polymers such as PEEK and nylon 12. The process at a high level is really simple and can be broken down into three main steps. So the first step, the printing process, involves feeding a set of long fiber carbon or glass fiber sheets into the printer. They are then used as effectively as a print bed. A clear binding fluid then is jetted onto the sheets using an inkjet head, and the polymer powder is deposited on top. This then adheres to the printing fluid and fibers underneath. The excess powder is then vacuumed off, recycled into the machine, and a powder coated layer is left behind. The process is then repeated for all subsequent layers. And the second phase is the heat and press. Once all of the layers are in place, the part is heated to the melting point of the polymer under a specific load. The particles melt and encase the fibers to fuse the layers together into a solid component. We then have the third phase, which is the material removal. As a final step, the unbonded portions of the fiber sheets are blasted away, revealing the geometry of the final component. Unlike chopped fiber parts, the resulting part is end-to-end reinforced with long fibers, providing an improved level of strength. The key components of the process can be broken down into two main areas that you can see on this table. We have the substrate, which is the woven sheet. This gives the primary source of the X and Y strength. Currently, we have carbon fiber and glass fiber as commercial materials. Other materials like Kevlar and polyesters have been trialed and are in the roadmap for the future. Secondly, we then have the polymer powder, which has two main functions. Initially, to bind the sheets together, and then secondly, to provide the strength in the Z-axis. There are very little constraints here, and basically, as long as the material can bind with the substrate and is in powder form and has a lower melting temperature than the substrate, it can be processed. So we have lots of capability. We then have the technology benefits. The printing process is extremely fast. We can print a full build in just a few hours, making the technology ideal for serial mass production applications. With a new generation of machine, the process will be even quicker. The powder-based process delivers high-strength parts that are stronger than all other polymer-based 3D printed materials on the market. This makes the technology ideal for metal replacement parts while reducing weight. You'll hear more about the materials in a couple of minutes from Enrico. However, you will learn that we can process a huge range of polymers and varying fibers. Now I'm going to pass you over to our material scientist, Enrico, who will go through the further detail on the materials.
Hello everyone, and thanks Mark for this general introduction about the technology. So, as Mark said, let's dive a little bit more in details on the material, some of the design guidelines for the process, and some use case for this technology. So, As Mark has said, and as we talk about composite material, we have two different type of materials that are used in this technology. The first one is the substrate, which could be either carbon fiber or glass fiber sheets at the moment. In the particular case of CBAM, the process uses non-woven sheets at the moment. These sheets are composed of long fibers that have a length between 12.5 and 25 millimeter. In the case of these sheets, the fibers are randomly oriented in the X and Y plane, as you can see in one of the picture here from a microscope image, and the fiber are bound together by a polymer binder. The other component used in the process is the polymer matrix, and currently the process can work from a commercial point of view with either nylon 12 or with a more high performance material like PEEK, which stands for polyether ketone. And if we look now at the mechanical properties we can achieve by combining those different material together, you can see that you can achieve parts with a very high tensile strength, which is generally above 100 megapascal for different material combination. Parts produced with PEEK and reinforced with carbon fiber, they have the higher tensile strength and the tensile modulus. Whereas if you need parts with a slightly higher elongation at break, of course, in this case, is not a very ductile material that you got. So generally, parts with reinforcements of glass fiber are the best option in this case. And as Mark mentioned before, the very high strength-weight ratio for this material make them a really good solution for metal replacements, more in particular for aluminum alloys. Talking about PEEK, which is also generally a material that is quite difficult to print. It's for me, it's a great material because it's a lot of benefits. In particular, a very high temperature resistance and dimensional stability, high temperature, as the melting point of the grade that we use in this technology is a melting point of around 340 degrees. And combined to these properties, PEEK has also got some excellent chemical resistance, a very good wear resistance, very good insulating properties, and it is also intrinsically flame retardant. However, although there are only these 4 materials available at the moment, looking more long term, there are more options that we can use both on the substrate material and on the polymer matrix as well. So from a substrate point of view, potentially you can use other type of fiber, both synthetic and natural fiber. We can use woven sheets, or also, for example, unidirectional fiber or fiber with even a higher length of the fiber itself. And for the polymer matrix, in reality, as long as you can have a powder that could flow and spread effectively onto the fiber, there is no other limitation apart from those that Mark mentioned in one of the previous slides. And actually, some of these combinations have already been tested at R&D level. For example, with materials like polypropylene, PA6, or even rubber and elastomer. Just these have not been scaled up at the moment. When so far we've seen mainly thermoplastic polymer matrix, but actually the process can also work with thermoset polymer matrix. For example, the thermoset powders, like the one that have been developed by Tiger Coatings under their digital 3D set range, can also be used in this process. And there is actually a collaboration, a partnership going on between Ricoh, Tiger Coatings, and Impossible Object. The main benefits of thermoset powders is the fact that they require lower processing temperature compared to thermoplastic powder, especially like PEEK. So the process speed is slightly faster than in the case of PEEK, for example. However, when you look at the mechanical properties of the carbon fiber reinforced thermoset material, you can see that the tensile strength and the modulus are even superior compared to those you can obtain with the PEEK-based counterparts. And again, the thermoset composite material have got a very good dimensional stability, high temperature, great chemical resistance, great insulation properties, and they're also flame retardant. So this range of material are really in the very last phase of development before being released commercially. But as you can see in the picture, like in the picture here on the slide, some large parts can already be printed, like it is the case for the central black part of this steering wheel. Which has also some additional element on it that has been printed. In particular, those blue, yellow, and red parts that have been again printed with thermoset-based carbon fiber reinforced material, and those parts have been finished with a powder coating specifically developed by Tiger Coatings for this material. So we've seen a bit of an overview of the material. Let's now have a look at some of the design rules that we need to keep in mind when designing or selecting parts for the process. As like with every manufacturing process, there are always some constraint from a design point of view associated with the technology. So from a mechanical point of view, the parts have anisotropic properties, meaning that the mechanical properties in X and Y, where the fiber are randomly aligned, will be higher than in the Z-axis, where the strength will be mainly provided by the polymer matrix. So it is important when designing the part to orient critical features or areas that will be submitted to mechanical load accordingly. Also, as Mark mentioned, when describing the different steps of the process, during the consolidation steps, the parts are heated under load. And once the load is removed, the fiber tend to expand like a bit like a spring. So this could lead to layer separation in the parts. So in order to avoid that layer separation, the fiber can be bound by printing some what we call support features, which are not exactly the same that support feature that people are familiar with when looking at some metal process or SLA process. And those support features actually are printed in unprinted areas, like in the image you can see here, the second image in the middle, and their function is just to keep the fiber together when you remove the load. So this risk of delamination has also an impact on the minimum features that can be printed with the technology. And as a rule of thumb, areas with a wall thickness below 3 millimeter will have a higher risk of delamination. This can be overcome by adding those support structure to alleviate stress in those areas and reduce the risk of delamination. And for areas that are thinner than 2 millimeters, there is still a risk of delamination even with support structure. Then, when it comes to fiber removal at the end of the process, it is important that the fiber are visible and accessible. So the parts must have a line of sight to every area from which the fibers need to be removed. In terms of other minimum features that can be produced, generally alls must have at least a 1 millimeter in diameter. It's impossible to create parts with texture on the surface, like embossing and engraving. And for this type of feature, it must have a 0.5 millimeter wide and 1 millimeter tall for a good definition. In terms of tolerances, the standard tolerances of this process as a first iteration are generally in the range of plus or minus 0.4 millimeter. However, this can be improved by iteration, as depending on part geometry, the level of shrinkage or expansion that you can have during or after the consolidation stage could be different. And in some cases, for a very specific geometry, the process has enabled to get parts with tolerances of plus or minus 0.1 millimeter after a few iterations. In terms of print volume, for each material there is a small and a large format, and as you can see, the maximum print size in X and Y is 280 millimeters, whereas the maximum height is between 50 and 100 millimeter, depending on the format you use in the process. So now, after we've had a look at some of the design guideline, let's have a look at some of the application and use case that have been enabled by the technology. In terms of verticals where parts printed with the CBAM technology have found application, we can see we have some of the most demanding industry in terms of material performance, or also application where reducing weight or the thermal and chemical resistance of the part are very important, such as aerospace, automotive, oil and gas, or industrial application. The technology have also found application in the electronic industry, in particular for the production of soldering fixture and pallets. And of course, the production of this type of fixtures or tools is not limited to the electronic industry, but this can be extended to any industry where durable, lightweight jigs, fixture or tools are required. On top of that, we've also seen application in the consumer industry, where for some application you have a need for high strength and high durability for the products. As mentioned in the previous slide, one of the main applications where this type of composite parts made with the technology have been very successful is the production of PCB solder pallets, soldering fixture, and generally high temperature tools for the electronic industry. In particular, with PEEK-based composite, thanks to the high temperature resistance and the low coefficient of thermal expansion of the material, this enables the use of a soldering iron on the fixture without damaging it, and which enables to hold the component in place during the process. And actually, the fixture, they don't get damaged during the process, and so they can be reused. And really, one of the benefits of the technology is that it enables to produce large and very flat part with no warping, which is something that is quite challenging with a material like PEEK, and also to keep the tolerances required by this type of application. Also, thanks to the speed of the process. The lead time could be reduced from several weeks to, in generally, 1 week to 10 days. And as there are no setup or tooling costs, it is also a very good solution for bespoke or low volume fixtures. Another very successful application for the CBAM technology is the production of functional propellers and impellers. In this case, thanks to the fact that you have an evenly distributed fiber content throughout the part, you are able to produce fully functional, high-strength point features and feathered edge that can actually withstand the rotational forces without breaking. So some of the customer we have been working on have tested some propellers and impellers made with the CBAM technology, and they've realized they can actually those parts can achieve a performance that is comparable to those produced by injection molded glass fiber reinforced PIC. And as mentioned before, the technology have also been used to produce parts in the consumer industry. And a first example that I want to showcase, and this is definitely one of my personal favorite, is the production of the so-called real whale surfboard fin. The design of this very, very unique fin is inspired by the fins of the humpback whale. It has been developed and optimized by Dave Shorman at a company called Dive in the United States in collaboration with the Surflex Lab in Australia. So unlike traditional fins that are, as you probably know, generally very, very smooth, this one has a lot more complex shape with a long and narrow shape with nodules along its leading edge and notches along its trailing edge. And before testing the CBAM technology, they tried different material, mainly reinforced SLA or reinforced SLS material, but the end result was always that the fin snapped after a few waves. So they decided to try to print the fin in carbon fiber reinforced PIC, also to try to achieve a higher strength and also maximize the stiffness of the component. And this has actually enabled to achieve a fin that can withstand thousands of waves without failure. So the durability of the part has been significantly improved. And in the end, compared to off-the-shelf fin, this real whale fin has also led to significant improvement in terms of performance in the surfing, in terms of increased length of ride, much better sharpness of turn, and also improved overall speed. And another interesting application still in the consumer market is the production of jewelry pieces by Jenny View as part of her lace collection. And again, in this case, the technology has enabled to produce some very unique and sinuous pieces that are very lightweight, durable, and can be produced as really bespoke items in term of size as well, and can be produced really on demand in a few days when a customer place an order. And lastly, in terms of use case, the one that I want to share is this one for Balio. So Balio is a robotic company in France that we have supported also with the small volume production of a connector for some electrical component for one of their autonomous lift trucks. In this case, the material used was glass fiber reinforced PIC. Originally, the part was designed to be made out of steel, and then by produced by a CNC machining process. But due to a change in the function of the part, they have to move from a conductive component to an insulating one. So one possible solution would have been to use a coated insulated metal part, but this would have been led in a part with a higher thickness and then small changes in the design. So by using a composite part instead, they managed to use the original design as the high strength and the insulating properties of the material allow to keep the original thickness. So we produced 160 units of this connector. You can see a picture of the full set of parts here. These were just producing in just a couple of weeks, providing a lead time that is 3 times shorter than a machine option for a reinforced material. And there was also a cost saving of around 30% compared again to a machined solution. And in the end, also the standard dimensional tolerances of the part, even just after the first iteration, were within the tolerances required by the application. So yeah, that's it for me. So over back to you, Mark, for the final remarks and conclusion of the presentation.
Thanks, Enrico. That was a great comprehensive overview of the technology. So to summarize the presentation, we believe that the CBAM technology is a unique 3D printing technology with lots and lots of potential. We're able to manufacture high-strength, commercially available PA12 and PEEK composite parts. The process is extremely fast, accurate, and which enables serial mass production applications. What the future holds for us and the technology, we believe there's huge opportunity for a wider range of materials and combinations to be validated on the CBAM process. Impossible Objects are already working on the next generation machine, which has a larger print volume, which will also include faster print speeds and lower part prices for all. So thank you very much for listening. We're going to now move on to the Q&A section. We've only got a couple of questions, so if there's anything that springs to mind following the webinar, please contact either Enrico or myself directly. So just to move to the first question that has been asked, how do we order and how can we get a sample of these composite parts? So
yeah, that's quite easy. You can just reach out to us at Ricoh 3D on our website, and we can facilitate that. Send you a sample, providing some additional information as well, all the technical data sheet, the design guidelines. We can give you all those information, and then yeah, it's pretty straightforward.
There's a lot of resources as well on the website, so, you know, the TDSs, and we're able to send some free samples out if you use the contact us function on the website. And then the next question was, what other materials are you currently working on?
Yeah, so as I mentioned, there is the thermoset material are the second, the next one on the list in terms of commercial material coming available, and then really Impossible Object, they work on an Ultem material as well. That it's a material that again they see a lot of potential. But generally, as I said, the material that can be processed on the technology is quite wide. So again, if you are interested in any specific material and you have high demand for a specific material, we can have a look at that and try things really.
Yeah, and I think it's going to be driven by the application and sort of, I know we hear this word a lot, the business case. If there is potential there, we will look. we'll definitely look at considering qualification of the material or substrate comparison. We've got a couple more questions coming in now. What percentage of the material accounts for the fibers?
So in the case of this technology, we are at around 30% in volume of fiber. But again, as I said, the fiber are long fiber, so generally you got a lot more fiber than what you get with, for example, material in FDM or SLS. They generally use chopped fiber.
Another question here is, you mentioned there's lots of potential for other materials. What do you find most suppliers are interested in? I think it's quite a difficult question, as you know, this technology is relatively new to the market, and we're seeing a higher interest for the PEEK carbon fiber combination. Shortly, we're going to be announcing the commercialization of the Thermoset, which we've already seen quite a high demand for. So I think again, it's going to depend on the application that the material is required for. But without doubt, at the moment, PEEK is the area of interest, mainly due to the competitiveness of the cost of those components. And then, is there a reason for 30%? Does the higher volume mean higher stiffness?
Again, it's a difficult one. Potentially, yes. Potentially, you can even go higher in stiffness by using different type of fiber. If you use unidirectional fiber, for example, you can increase the stiffness in a specific direction. It's not really something that is optimized. The content of fiber, that's sort of given by the process itself. But again, there is room to play by using different type of fiber on increasing or reducing the stiffness of the component.
I think that is all. That we're in a position now to close the webinar. Like I mentioned, if there's any further questions, please reach out. And thanks for listening.
Thank you very much. Bye, everyone.